Okay, so let's dive into what is honestly one of the most powerful ideas in all of math and science. It's this concept that reveals a kind of hidden structure to the world, a secret recipe, if you will, that describes everything from the sound of a piano to the photos on your phone.
Yeah, I know. It sounds like a trick question, right? One is sound, a vibration in the air that changes over time. The other is a completely static visual image, just a grid of pixels. But the answer connects them in this incredibly profound way, and it's actually fundamental to how our digital world really works.
And that right there, that's the core concept. Think of it like this. A fancy meal at a restaurant might seem super complex, but really, it's just a specific recipe made from basic ingredients. Well, Fourier discovered the exact same thing is true for signals. Any complex signal, whether it's a sound, a picture, a radio wave, can be broken down into a recipe of really simple, pure waves.
So this whole game-changing idea comes from a French mathematician, Joseph Fourier. He was actually studying how heat moves around, and he had this massive realization. You can describe almost any complex, messy function just by adding up a bunch of simple, predictable sine and cosine waves. You can think of these as like the purest, simplest notes in the universe, just smooth, perfect, repeating waves.
So not only did he have the big idea, he figured out the master recipe book. He found the method to calculate the exact amount of each simple wave you'd need. Now, this recipe comes in two main flavors, and we're going to start with the one for things that repeat themselves. All right, so for our first tool, the key idea is periodicity. Just think of anything with a repeating pattern. The constant hum of your air conditioner, the orbit of a planet, a steady note from a violin. For these kinds of signals, we use something called the Fourier series.
A good analogy is a musical chord. A C major chord sounds like one complex thing, but it's really just three specific, pure notes being played at the same time, C, E, and G. Well, the Fourier series gives us the exact notes, those sine and cosine waves, that add up to create any repeating signal.
Okay, now this is where it gets really fun, because you can see the recipe in action. A square wave looks nothing like a smooth sine wave, right? It's all sharp corners. But check this out. If you just follow Fourier's recipe, adding simple waves of different speeds, we call them harmonics, this sharp, boxy shape just starts to appear out of the mix. It's basically mathematical alchemy.
So the Fourier series is fantastic for those repeating signals. But let's be honest, most of the world isn't that neat and tidy. A hand clap is a sudden burst of sound. It doesn't repeat. A photograph doesn't have a repeating pattern. This limitation meant we needed a bigger, more powerful tool.
And this brings us to the master tool. If the Fourier series is like a recipe book for repeating cakes, then the Fourier transform, well, that's the universal encyclopedia for cooking anything.
The transform is the ultimate upgrade. It takes any signal, repeating or not, and gives you its complete frequency recipe. It's like shifting your whole perspective. Instead of watching something happen over time, what we call that time domain, you're suddenly just looking at the final list of all the ingredients, the frequency domain. And this table here just lays it all out perfectly. Let's walk through it. See the type of signal? The series is picky, only periodic signals. But the transform, it'll take anything, periodic or aperiodic. Now, look at the result. The series gives you a few specific ingredients, those nice, neat spikes at certain frequencies. But the transform gives you the whole nutritional label, a full continuous spectrum of every single frequency inside that signal.
Okay, so this is a 200-year-old math idea. Why should you actually care? Well, because you are literally using it right now. It is invisibly woven into almost all of our modern tech.
Seriously, this isn't just some abstract theory. It's the foundational toolkit for electrical engineering, for computer science, for physics. Everything from filtering the noise out of your phone call to how an MRI machine creates a picture of your brain, Fourier's recipe is in there, working behind the scenes. Let's go back to that JPEG image we talked about. The algorithm literally breaks the image down into its frequency recipe. Sharp edges and tiny details, those are high frequencies. Smooth areas of color, low frequencies. So to compress the file, the algorithm just throws away the high-frequency information our eyes are less sensitive to anyway. It's ditching the least important ingredients to make the recipe smaller, and you barely even notice the difference in taste.
And this connection goes even deeper. I mean, all the way to the heart of physics. This quote is describing a fundamental trade-off that exists in reality itself. A very short, sharp signal, like that single hand clap, is really concentrated in time. Its frequency recipe, its Fourier transform, is incredibly spread out, made up of a huge range of frequencies. And get this, that mathematical relationship is the exact same principle behind Heisenberg's uncertainty principle in quantum mechanics, the one that says you can't know a particle's exact position and its exact momentum at the same time. It's the same math.
So, in the end, Fourier analysis gives us this incredible new lens to see the world. It shows us that underneath the surface of time and space, there's this hidden dimension of frequency. It teaches us that even the most complex things can be understood as a symphony of simple, pure waves. And that really just leaves one question, doesn't it? What else can we find the recipe for?